In engineering, there's this one critical property that pretty much dictates cost, speed, and quality. It's called machinability. Honestly, it's the difference between a part that comes out perfectly and a project that just completely goes off the rails. So today, we're going to break down exactly what factors control it.
It's a great question, isn't it? Why is it you can slice through a block of aluminum like it's butter, but then you try to cut an advanced superalloy and it just fights back, destroying your tools and giving you a massive headache? That's really the core of what we're digging into today.
And we're going to tackle this almost like lecture notes. First up, we'll nail down what machinability even is. Then we're diving into its three main pillars: what the material looks like on the inside, the crazy physics of heat right at the cutting edge, and finally, the brute force of its own toughness. And then we'll see how it all fits together.
So, let's start at the very beginning. Before we can really get into why some materials are such a pain to work with, we all need to be on the same page about what machinability actually means.
At its heart, machinability is just a measure of how easy something is to work with. I mean, the dream scenario is a material that cuts smoothly, leaves a beautiful surface finish, and is super gentle on your tools, all without needing a ton of force. That perfect combo, that's what we call good machinability.
And believe me, this isn't just some abstract theory. It has huge, real-world consequences. Poor machinability means you're constantly swapping out expensive tools, which drives your costs way up. It means you have to slow down production, and that kills your efficiency. And it can even compromise the quality of the final part. It's one of those things that can really make or break a whole manufacturing process.
Okay, so what's the first pillar of machinability? Well, to really get why a material behaves the way it does, we have to go microscopic. We've got to take a look at its internal structure.
Think of it kind of like the grain in a piece of wood, but on a much, much smaller scale. You see, a block of metal isn't just one solid thing. It's made up of a ton of tiny crystals, or what we call grains. The size, the shape, how they're all packed together, plus any other hard little particles mixed in, all of that creates this unique landscape that a cutting tool has to literally fight its way through.
And here's a perfect example of what I'm talking about. This research from Konya and Kovacs points out that materials like nickel superalloys are packed with these incredibly hard particles called carbide precipitates. Just imagine trying to cut through something that has tiny bits of ceramic embedded all through it. It's basically like running your cutting tool over sandpaper. It just gets ground away.
And you can see how different materials present their own unique challenges. Take T6Al4V, a big aerospace alloy. It has what's called a dual-phase structure, two different crystal types mixed together, which gives it amazing strength but makes it hard to machine. Then you have something like Inconel 17. It's reinforced with these tiny particles called gamma prime, making it ridiculously strong but also really resistant to being cut. Every microstructure is its own little puzzle.
But here's the really cool part. We can actually change a material's microstructure. Research on 3D printed Inconel 718 shows this perfectly. Right out of the printer, in its as-built state, it has this coarse structure with tons of internal stress, which is just awful for tool life. But after a simple heat treatment, that structure gets finer and way less stressed. And that finer grain structure lets the tool make a smoother cut, which dramatically improves its machinability.
Okay, so the material's internal landscape is pillar number one. But what happens when you introduce the intense friction of the cut itself? Well, that brings us to our second huge factor: heat. The way a material handles intense heat is every bit as crucial as its structure.
You know, a lot of these high-performance alloys, like titanium and nickel superalloys, are actually designed to be amazing thermal insulators. That's a fantastic quality if you're building a jet engine, but it is a total disaster for machining. Because they don't conduct heat away, all that energy from the cutting action gets trapped and concentrated right at the fragile little tip of the cutting tool.
And this kicks off a really nasty feedback loop. First, the material traps the heat. Second, the temperature in that tiny cutting zone just skyrockets. Third, the cutting tool itself starts to soften, losing its hardness and sharp edge. And fourth, that now dull tool creates even more friction, which generates even more heat, and the cycle just gets faster and faster until the tool completely fails.
So what do? Well, engineers have to get really aggressive about fighting this heat. As you can see from the research, the cooling strategy you pick is everything. Machining dry is pretty much a recipe for failure. Using something called minimum quantity lubrication, or MQL, is better, but for the really tough stuff like the GH4169 alloy, you've got to pull out the big guns, like high-pressure cooling, to literally blast the heat away from the cut and keep that tool alive. All right, that brings us to our third and final pillar. We've looked at the material's internal structure and how it deals with heat.
Now let's talk about its raw brute strength, its natural toughness and resistance to wear.
This quote from research on Nimax mold steel just sums it up perfectly. The very things that make a material great for its final job, like being super strong and tough, are the exact same things that make it a total nightmare to machine. The material is literally designed to resist being changed or worn down.
So what does that actually mean when you're cutting? Well, it means you need a ton of force just to make the cut, which puts a huge strain on the whole machine. That directly makes the tool wear out faster and can cause vibrations that wreck the surface finish. It also leads to this really common type of failure called flank wear, where the side of the tool literally gets worn away by the intense friction.
And this is how it all comes together. See, when a tool finally fails, it's almost never just one thing. It's a combination of all three of these factors we've been talking about. Abrasive wear from the material's hard guts, thermal softening from all that trapped heat, and the sheer force you needed to overcome its toughness.
Okay, so we've looked at all the individual pieces. Let's take a second now to put the entire machinability puzzle together so we can see the whole picture.
So if you remember anything, remember this. The machinability of any material really comes down to these three connected pillars. Number 1, its internal microstructure and hardness, what it's actually made of. Number 2, its ability to get heat away from the cut. And number 3, its raw toughness and resistance to wear. If you can get a handle on these three, you can get a handle on machinability.
And this is exactly why it all matters. Understanding these pillars is what separates failure from success. It's how engineers pick the right tool for the job, design the best cooling strategy, and dial in the perfect parameters to turn a so-called difficult-to-cut material into a perfect, high-quality part.
And that kind of leaves us with a final thought for the future. You know, the demand for better materials is never going to stop. We are constantly pushing the limits to create alloys that are stronger, lighter, and can survive more extreme conditions. The challenge, then, is that for every amazing new super alloy we invent, our machining techniques have to evolve right alongside it. And that's the puzzle we're going to be solving for decades to come.